listening to Worth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Worth Electronic technical specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast. If the output filter is implemented in the control section, the control section is second order. This is something we discussed in last week's episode, Loss-Free Filter. Well, in today's episode, we are discussing the control loop of the second order. This is where the output filter is integrated into the control loop. But this means the switching regulator must be operated with a higher integral action coefficient that dampens the control loop and makes it slower. So the output voltage of switching regulators has a voltage ripple that can disturb with electrical power supplied circuits and lead to electromagnetic disturbances. Thus, output filters are often used for noise suppression, which may, under certain circumstances, have an influence on the control loop. To prevent output power losses, it may be necessary to compensate the control loop. No matter what switching regulator topology is used, as a result of the parasitic series resistor ESR and the parasitic inductance ESL of the output capacitor, the output current causes an undesired residual ripple. Depending on the capacitor type selected, a relatively large residual ripple is created, which has varying waveforms. A common electrolytic capacitor, for example, can have a ripple voltage of up to a few hundred millivolt, depending on the output power of the switching regulator. If a ceramic capacitor is chosen, then the ripple voltage may only be a few tenths of a volt. A high residual ripple is undesired and it can cause disturbances with electrical power supplied circuits. In particular, analog and high-frequency circuits require a stable, smooth, and clean supply voltage. Nevertheless, the high-frequency component of output voltage harmonics, which can give rise to increased electromagnetic interference, must also be taken into consideration. An output filter is able to reduce residual ripple and filter out high-frequency components. LC low-pass filters are usually used in practical applications to reduce the residual ripple. If a particularly clean output voltage is required, then the LC low-pass filter is expanded with a further low-pass filter that comprises of a ferrite and a capacitor. Figure 1 attached in this podcast depicts a two-stage output filter, which can actually be made up cost-effectively using the WE PD2 coil and a surface mount ferrite, the WE MPSB from Worth Electronic. In our image of this two-stage output filter, we see that L subfilter and C subfilter 1 act as a low-pass filter, which filters out the clock frequency of the switching regulator and smooths its harmonics. Further high-frequency components of the switching regulator output voltage are converted into heat by the surface mount ferrite, and, together with C subfilter 2, their amplitude is damped. A simple output filter of this kind reduces the residual ripple to only a few millivolts and can be used in power supplies even for radio-controlled circuits. From a certain output power of the switching regulator, the output filter causes significant DC losses in the output power, and thus a reduction in efficiency of the switching regulator. The DC resistance, or RDC, of the coils and ferrites now causes a significant voltage drop across the output filter, which results in a reduction of the final output voltage. Depending on the type of coil used, the RDC can be between a few milliohm up to a few ohm, which is not negligible at high output currents. Even a surface mount high current ferrite could have a DC resistance of up to 0.04 ohms. To determine the actual voltage, the output voltage of switching regulators is taken from a voltage divider and is connected to the feedback in the switching regulator IC. In order to reduce losses in input voltage through an output filter, it's possible to include the output filter into the control loop in that the actual value is taken at the output of the filter. Our attached figure 2 of this podcast shows the schematic arrangement for this method. So our problem now is that the filter coil, the ferrite, and the filter capacitors cause an unwanted phase shift, which interferes with the stability of the converter. This unwanted phase shift leads to the reduction of gain margin and phase margin. In extreme cases, this leads to instability, and the output voltage tends to oscillate. To ensure stability, a gain margin of greater than 12 decibels and a phase margin of greater than 45 degrees is required in practical applications so that the control loop does not tend towards oscillation of any kind of disturbances. The control loop is deemed to be dynamically stable if the loop gain is 0 decibels before the respective phase shift has reached negative 180 degrees. Here, the amplitude response of the loop gain should extend through the intersection of the x-axis, that is, at 0 decibels, with 20 decibels per decade. In our attached figure 3, we can see a Bode plot of a stabilized buck converter. This example shows a gain margin of 32 decibels and a phase margin of 56 degrees. If the stability criteria of a switching regulator with output filter are not met, compensation of the control loop is required to ensure a stable output voltage. If there is a change in voltage at the input of the switching regulator, the output voltage must remain stable. Same as in the instance of a sudden drop or rise of the output current, the output voltage must be stable again quickly. This is called transient response. We can see the transient response of a stabilized switching regulator in our attached figure 4 in this podcast. Here we see the yellow trace at an output voltage of 5 volts and a sudden load change from 0 amps to 1 amp as seen in the green trace. A sudden load change needs to cause a fast transient response of the control loop so the output voltage is returned quickly to its set point value. The transient response must not cause high voltage overshoot in the output voltage. If it does, then subsequent components could be destroyed at too high voltage. In an ideal situation, after the voltage drop, the output voltage should be brought back quickly to the set point value without overshooting or ringing. A ringing during the equalization phase means that there is an instability of the switching regulator. If a quick step response and a timely equalization phase are achieved, the switching regulator is deemed to be stabilized. In short, if the output filter is integrated into the control loop, then this is called a control loop of the second order. This means the switching regulator must be operated with a higher integral action coefficient, which dampens the control loop and makes it slower. This now requires a more complex compensation of the control loop. Thus, the method of including the output filter into the control loop is not recommended. The output voltage of the switching regulator should be taken at the output capacitor of the switching regulator in front of an output filter. To reduce DC losses due to the output filter, it's recommended to select filter coils and ferrites with the smallest possible DC resistance. Attached images are available in most podcast streaming networks. To view all images, visit www.we-online.com/podcast. To download the complete application note we discussed today, visit Worth Electronic online at www.we-online.com/appnotes. You're listening to Worth Electronics What's Up Radio Podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists who will shine a light on our topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up Podcast.